But first, we coffee. I don't know why people are so interested in what I drink, but they continue to ask, so here it is. 5 grams of creatine, 2 shots of cold brew, and a vanilla protein shake. Let me go grab some ice and we can get started. Welcome back to Cloud 42. I'm James. Well, I have been promising for a while that I would put together some recommendations for stepper or servo motors for the electronic lead screw. And the more research I do, the more motors I look at, the more spec sheets I read, the more I realize that this is a confusing topic for a lot of people. So I've been slowly acquiring some different motor options, and I think it's time we finally get around to doing some testing. Here are 3 of the motors that I have acquired for testing. And I've got them in order here from least expensive to most awesome. The first option here is a straight stepper motor. This one is from Stepper Online, and this is a very inexpensive motor. I think the motor itself is about $35, and you can get a driver that can run this for not much more. So you're definitely sub $100 and maybe a lot under $100 for a stepper motor of this caliber and a driver for it. Now they advertise this one as 566 ounce inches, which is about 4 Newton meters. It's possible to get that kind of torque in a motor this size. I don't know if you can do that continuously without overheating it. And I think you're definitely going to be losing a lot of torque on the high speed end of the curve. We will do some testing and determine what the capabilities of this motor really are. The next step up from this though, because this is a stepper motor, it doesn't provide any feedback to the controller. So the driver and the controlling system have no idea if this thing loses steps. If you put too much load on it, it will fail to step when commanded, it will get behind, and the system will have no idea that that's happened. And so on the electronic lead screw, your threads will get out of sync and you'll wreck your part. And again, the system, there's no warning that that's happened unless you happen to hear it happening. The next option is what's called a closed loop stepper. This is a stepper motor, same as this, except that it has an encoder under this cover on the back and an additional cable that goes back to the driver to feedback the position of the motor. So the driver will know if you have overwhelmed the torque capability of the motor, and it can send additional steps to catch up. Now, of course, you can just overwhelm the capabilities of the motor so it can't catch up, but in that case, the system does have feedback and does know that steps were lost and can respond accordingly. These motors are, of course, more expensive, but not that much more. The prices are really coming down. This one is from Automation Technology, and this is their 3 Newton meter version, which is something they've just recently added to their lineup. I actually have their older 2 Newton meter version over on the lathe right now. We'll also pull that off and do some comparison testing with that. The stepper motor with the driver for this runs somewhere between $150 and $200. So it's more expensive than a straight stepper, but it should provide a lot more capability. Now, it's still a stepper motor, so it's still going to sing. You're still going to hear the typical sounds of a stepper motor. It's not going to be as smooth as a true servo. It's not going to have as much torque at higher speeds, but it should be a much more capable than just a stepper. And speaking of true servos, that's what I have here. This is a ClearPath servo. This is their 8 Newton meter NEMA23, which is the most torque that they make in the NEMA23 package. This is their slow speed winding, so this will go up to about 1800 RPM. And this is not a stepper motor. This is a true servo. So I believe this is like a 3-phase AC brushless servo motor. Don't quote me on that. But the encoder's on the back with the control electronics on board. And because this is not a stepper, it does not lose torque at higher speeds. So this should be able to maintain its full torque, right up to its max RPM of 1800 RPM for this model. Now, you pay for that capability. This one is quite a bit more expensive. If we're talking $150 to $200 for the closed loop stepper, this motor alone, which does include the driver, is about $350. And by the time you add their 72 volt power supply and their custom cables and shipping, you could be looking at $650 for a single servo setup like what we need for the electronic Leadscrew. Is that worth it? Well, we'll do some testing and find out. Now these are all NEMA23 or NEMA24, we won't get into that, motor frames, so they should be physically interchangeable and fit in the same mounts. However, they have seen fit to use different motor shafts. These 2 Newton meter and 3 Newton meter motors from Automation Technologies have a 1/4 inch D shaft with a single flat. The NEMA24s from Stepper Online have an 8 millimeter D shaft with a single flat. And the ClearPath is a really strange combo that I have never seen before. This is a 3/8 inch shaft, 375 thousandths, so it's an imperial shaft with a 3 millimeter keyway in it. I have no idea. I asked them where on earth I'm supposed to get pulleys or couplers that fit a 375 shaft with a 3 millimeter keyway, and they said they have no idea. It's historical reasons, and they just recommended using clamp-on pulleys. Of course, I can't find clamp-on pulleys in the 3 millimeter HTD belt pitch that I'm using, so I will just go ahead and make something for it. Now what I'd like to do is set these up and do some torque testing. How do you do torque testing on motors? Well, there's lots of very high-end, very expensive equipment to do it, but I think we can rig up something much simpler. What I want to do is just put a spool on the shaft of the motor, wrap a line around it, and rotate the motor to pull on that line and gradually increase the force that's resisting that motion until the motor stalls. And if we know the radius of that spool and the amount of force on the line, then we can calculate the stall torque of the motor. We can repeat that test at different speeds, and we can characterize the torque curve of the motor. So I'm going to make some spools. These are going to be 80 millimeters across the functional diameter, giving us a radius of 40 millimeters, which conveniently is 1/25 of a meter, which should make the math easy. These would be 26 millimeters thick, and we'll need to make one for each motor shaft that we want to test. So 1/4 inch, 3/8 with a keyway, and 8 millimeters, all with a single locking screw to hold it on. And those parts are hiding inside of this piece of aluminum. Let's go over on the lathe and cut them out. When it comes time to mount the motors on the lathe for testing, I'm going to need 3 millimeter pitch HTD pulleys for them. And I was able to just buy pulleys for all of the motor shafts except for the 3/8 inch with the keyway in it. Closest I was able to find was an 8 millimeter pulley. And as long as I've still got the collet chuck here in the lathe, we'll go ahead and mount this and just bore this out to 3/8 of an inch, and we'll broach a keyway in it later. Got a 3 millimeter collet in here. Snug that down, and let's just do a quick sanity test, sanity check, just to make sure that it's not, wobbling all over the place. 3 thou is plenty close enough for a pulley. I've got a little Criterion boring bar here, and let's just go ahead and take a skim cut, see where we are, and we'll bore this out to the right size, get it close, and then we'll run a reamer through it to get it to exactly 3/8 of an inch. Okay, there's 365, we're within 10 thou. Let me grab the reamer. That should be that. Got a 375 gauge pin here. And it just slides in. I think we're good to go. Okay, I lopped off a hunk of that aluminum bar. This is 3.5 inches in diameter. And I've taken just enough that I should be able to get 2 spools and then have some material in between that I can use to have some space to cut them apart. Put this in the 3-jaw chuck. Get a pretty good grip on this because I don't know how well it's going to be balanced. Start slow. I can live with that. And let's start by facing off the saw cut. Okay, that looks pretty good. Let's go ahead and put some blue Sharpie on here. There's no sense marking all the diameters or all of the different positions on this because I'm going to turn it down. I'll mark it again after I do that. We're headed down for 84 millimeters, but it doesn't make sense for me to measure in millimeters because I have inch graduations on my dials. So I'll go ahead and turn to 3,307. And I'm at 3,508 now. So I got a couple hundred thou to take off. Okay, that's exactly on size. Let's go ahead and blue up and mark where we need to carve this out. It's 3 millimeters and 23 millimeters. Yep, I know this angers the internet trolls, but it's aluminum. Now to get in here and dig this out, I am going to use a right-hand tool, and I'm going to flip it around so that my 80-degree diamond tool profile is more or less centered straight in. And let me make sure that I'm going to clear everything. Yep, I think so. Okay, let's do a little bit of carving. We're going to carve the center of this down to 80 millimeters, which is 3.15 inches. So I will just set my caliper here to 80 millimeters. I will zero it on incremental, and then I'll switch to inches, and this will tell me how much further I have to go. First thing I want to do, though, is just carve out and establish my width. And that should be 80 millimeters. On the dot. Could not ask for more than that. Okay, now we just need to drill this thing, and let's do this one 1/4 inch. Okay, that's one spool. The only thing we have to do is cut it off, and what we'll do is cut this in half in the bandsaw and then bring it back, flip it around, and face the other side. But while I've still got this stock on here, I will flip it around, chuck it back up, and we will machine another spool on the other side of it. And once I'm done with that, I'll slice it in half, and I'll come back and do the facing operation. Okay, I took these over to the saw and cut them apart. And now we just need to face off the reverse side, remove the saw cut. And we'll start with just a cleanup cut. See where we are. We're headed for 26 millimeters, and we've got 87 thou to go. And again, what I did is I set my calipers to 26 millimeters, zeroed the incremental, then I can switch to inches because I have inch graduations on my dials here. So I can see that I've got 86.5 to go. And there we are, we're under by 1 thou. I will take that. Now to make this part a little nicer to handle, let's put some happy little chamfers. That spool should be ready to go. I've just got 2 more to do. Okay, I've got all of the parts faced to width. This is the one with the 3/8 inch hole, so let's go ahead and put in the 3 millimeter keyway. To put in the keyway, I'm going to use a keyway brooch. This is a 3 millimeter A size keyway brooch, picked up from McMaster Carr, and picked up a 3/8 inch A size brooch bushing. So I should be able to just drop the brooch bushing in the hole. put the brooch into the bushing and just force it through with my arbor press. The one problem that you can see here is that my arbor press is a little half-ton model, is not tall enough to fit this. So I'm going to have to start it over here with the vise. This is not ideal. I do not recommend this, but I'm going to make it work. And the reason this is not ideal is because it puts sideways force on the brooch and will apply a bending load, which again is not what you want. But we can put it partway through this way. It just dug into the copper here, so. And there we go. After much pain and doing everything the wrong way, go ahead and write down in the comments everything I did wrong. I hope you were keeping score. We do have a keyway. And I already ran a keyway in the pulley that we reamed out to 8mm earlier, so these should be ready to go. Let's go over to the mill and put in the set screws. Well, we've got all of the pulleys made, and I have to say I'm pretty pleased. I'm impressed with how they came out, and that keyway was yeah, that was no fun. I definitely need to get a proper arbor press for broaching keyways, and I will work on that. But we got it done, no matter how ugly it was, and we didn't break anything. So now we need to drill and tap a hole for a set screw to ride on top of that keyway. And for the other spools, it'll just ride on the flat of the D shaft. So I'm over here at the mill. I've got my vise set up. Since there is a gap in the center here and the nut would contact this, I'm going to go ahead and set a parallel in the bottom. It's a 1-inch parallel, 26mm thickness on the spool, so that will be perfect. And we'll just drop it in here. Now I've got 3 of these to do, and I only want to do all the edge finding once. So I went ahead and set up a stop here in the vise, so this will roll over against it. So let me just get this snug. Now that would be sufficient for any of the other pulleys, but since this one has the keyway, I need to make sure that that's oriented at the top. And I played around with some different ways of doing this. You could, I played around with like putting a key in there that sticks out that I could try to, indicate off of, or try to put in a gauge block. And ultimately decided it just wasn't worth it. And the keyway itself is just kind of however the brooch rode in the bore, so it's not necessarily square to anything. So we will just call that good enough. Now I need bring in an edge finder here and find the center by indicating off of the 2 sides and using the half function, and then we'll indicate off of the front and come back 8mm to locate the hole. And we'll use the larger of the 2 diameters on this edge finder, which is 10mm. Now I am edge finding off of the front of this, which is normally not advised. Normally you would edge find off of the vise, but since my dimensions are from one side or the other, I need to go in 8mm. I've chosen to do that from the front just to make it a little bit easier for you to see so that the action isn't all buried here in the back. So that is my 0. Since this is a 10mm diameter, I will just set Y to 5mm. Plus or minus. So we're set to -5. So if I bring this up and then dial back to 0, we should be right on that edge. And we are. And we'll go in 8mm because that's where we want the hole. Let's start with a spotting drill. And we'll go ahead and try to capture most of the point of the drill just so that we will not have to chamfer after drilling the clearance hole. And we'll bring in a number 8 drill, which is going to be a clearance hole because I don't want to tap this all the way through. There's no reason that I need that length of thread. So we're going to drill down about an inch of a clearance hole that will actually clear the body of the tap, and then we'll drill the rest of it through with the actual tapping drill and just tap the bottom, I don't know, centimeter or so of the hole. Like how I'm mixing units, that way I anger everybody at the same time. And the battery in my Quill DRO is dead, so we'll do it the old-fashioned way. Okay, that's the clearance hole. And now let's run the tapping drill through. This is a number 21 because I've opted to use 1032 for this. Why 1032 when everything else is metric? Because I have a bunch of 1032 set screws, so we're going to use them. Okay, and the last operation is tapping, and I'm going to use a spiral point tap instead of my usual favorite spiral flute tap, because the spiral point tap will push the shavings down and out the bottom of the hole so that they won't come up and try to jam in next to the very tight fit of the tap in the clearance hole. And we'll run this as slow as we can because we don't have a lot of room for error if I overshoot. Okay. And that is that. Now let me just do the other two. And here are the finished spools. I'm pretty happy with how this turned out. The clearance hole ended up perfect. You can kind of see around the top there. They've got a little bit of a chamfer from the spotting drill. And all these just went uneventfully. I was pretty happy with it. Now with the 1/4-inch spotting drill, I was still getting a little bit of vibration from that mill. And again, it is a round surface, but this is a soft material and the cutting forces should have been really low, especially on a large diameter like that. So I'm going to have to look into what's going on there. Anyway, I've got some 1032 set screws here. Let's do some assembly. And that is perfect. Nice and smooth, runs nice and centered. Let's try the other ones. This is the 1/4-inch shaft. That looks good, and the 8mm. That's beautiful as well. Totally hear the stepper. Okay, we've got spools that now fit all of the different motor shafts. Now I just need to get a push-pull force sensor and some cord that'll go around this. It'll handle the forces involved, and we can get set up and do some testing. And we will continue working on that next time. If you enjoyed this video, if you learned something, give it a thumbs up. Feel free to subscribe to the channel and leave me a comment. I'd like to know what you think. Thank you for watching. Very anxious to see what these expensive ClearPath servos can do.